Hello, and in this last short video for now about diodes, I want to introduce the concept of the reverse biased diode. Now, I'm not talking here about Zener diodes in breakdown, just normal diodes connected up in reverse bias. A circuit like this. Now, you might wonder why anybody would do that. We have here a normal diode, which is in reverse bias. The current is trying to flow through in, if you like, the wrong direction. That means that only a very small amount of current, the saturation current, will flow in this diode. If the saturation current is, say, 1 nanoamp, then a voltage of 1000 times that, or 1 microvolt, would appear across this 1K resistor. That 1 microvolt would be amplified by this amplifier and output from the circuit. What is the point of building a circuit which outputs an amplified version of 1 microvolt? Well, I can think of two reasons why you might want to do this. First reason goes back to considering why this saturation current exists at all. Now, if you remember, the saturation current occurs because we have not a zero population of electrons in the conduction band near the junction, but because of the Fermi Dirac distribution, there is a small number of mobile electrons up there. And there'd be a small number of holes, vacant states, down in the top of the valence band. This is energy. This would be kind of distance through the diode. Oops. Sorry. Now, the Fermi Dirac distribution, you might remember, says that the probability that a state is occupied is equal to 1 over e to the power of the difference in the energy of that state to a fixed energy level called the Fermi level, divided by kT, plus 1. For a reverse biased PN junction, just at the junction itself, the Fermi level will be about halfway between the valence band and the conduction band, be about there. Now, the interesting thing about this equation is this term here, T, the absolute temperature. The formula suggests that as T increases, then the value of e to the power of e minus the Fermi level divided by kT will decrease. And if this decreases, then the probability of occupation of these states will increase. So as temperature goes up, you will get more mobile electrons up here and more vacant states down there, and a greater current can therefore flow. So the saturation current turns out to be quite a strong function of temperature. In other words, build this circuit here, and you've built a thermometer, a temperature sensor. There are lots of ways of building temperature sensors out of electronic components, but this is one. The other, and perhaps more common reason why you might want to build a circuit like this is if you're using not a normal diode, but something similar to an LED, a light-emitting diode. Well, remember that LEDs, light-emitting diodes, work by the electrons in the conduction band jumping down to the vacant states in the top of the valence band and releasing their energy in the form of photons of light as they do so. Well, this process can work in reverse as well. If you take a semiconductor diode and you build it so that there is an optical path for photons to come from the outside world into the junction, then photons can arrive, hit electrons at the top of the valence band, and give them enough energy to move up to the bottom of the conduction band. And as soon as they're up in the bottom of the conduction band, they can move, and we can get current, called a photocurrent, to current related to the amount of light that is appearing on the diode. You can buy components specifically designed to do this. They're called photodiodes. In fact, any light-emitting diode will work as a photodiode. If you put it in reverse bias, the saturation current that you will get out, the small reverse current, is a function of how much light is shining on the LED. But if you want this function, it is rather better to use a specially designed photodiode. That's the last of these short talks about diodes for now. We'll return to the subject later when we'll look at some more examples of real diodes and see how their behaviour differs from these ideal diodes that we've been discussing so far. And we'll also be looking at their use in nonlinear op-amp circuits. Circuits which, amongst other things, can tell you the signal strength of an audio signal that arrives at a circuit.